All right, so we were talking last time about implicit differentiation, and I want to talk about that a little bit more, both with just generic XY equations and then with related rates. But I also want to show you how you can use implicit differentiation to prove a couple of the derivative rules and, well, then extend it to, I'll use it on a couple of examples, but you can extend it to prove a bunch of the derivative rules that we learned earlier before our mastery test and just kind of took for granted, said we'll talk about why this is later. It uses implicit differentiation, which I didn't want to go through this technique of implicit differentiation prior to the mastery, just because it's essentially, it's just an extension of chain rule, but messier. And in order to get solutions, it does involve doing algebra and solving, unlike all the other questions where I asked you to not do algebra and just strictly take the derivative and then stop. So here's an equation relationship here. This is an equation of a circle with radius 10 centered at the origin. So maybe that looks like something familiar to you, maybe not. But in any case, we can find dy dx. If you think about, circles, we had a lot of circles we were dealing with for trig purposes recently, centered at the origin. But at any point on this circle, I can talk about how moving a little bit within an immediate area affects the changes in y and x respectively. So there should be a way to express the rate of change, dy over dx, how much y changes per change in x, as long as you're given a full coordinate point, like the precise location x comma y, as opposed to, since it's not a function, just being given an x value. Because when you're given a function and x is the name of the independent variable, being given x means that you also know y. You know the output when you know the input. You know the dependent quantity because it depends on the independent quantity. In other sorts of relationships, it doesn't. So there are multiple pairs, so I can't uniquely determine a y from just an x. But for instance, if I want to find this, I could use implicit differentiation, or I could solve for y. I could do either just as easy as the other. Well, you might see implicit differentiation is actually a bit easier. So what we talked about last time is if I want to find a derivative of y with respect to x, I have an equation that has x's and y's in it, but I have to differentiate with respect to x if I ever hope to get something like this. So I'm going to do the algebra trick, take the derivative of both sides with respect to x. So if this expression equals that one, then the rate of change with respect to x must be equal also. And you can see that, oh, well, the right-hand side changes overall at a rate of 0 with respect to x. The left-hand side then must also, but it has two component parts. The derivative of x squared with respect to x is 2x. The derivative of y squared with respect to x. Now, what we talked about last time, if you want to think of y as being f of x, an implicitly defined relationship, taking the derivative of y squared is like taking the derivative of a whole function squared. Its derivative is going to be 2 times itself to the first power, but then needing chain rule. And the derivative of f of x we'd write as f prime of x. The derivative of y with respect to x is specifically dy over dx. So this isn't the answer to find dy dx, but now we've done the operations that make that possible. All we have left to do is just some algebra. This is kind of similar to if you have 3x minus 4y equals 7 in algebra 1 and it says find y. Not the internet joke where you say, oh, there it is, that's y. It just means isolate it. So isolate dy dx. That's the only step we have left here, which is subtract and divide. You can probably do it all in one step because I know you're pretty good at algebra. Just be negative 2x and then divide that by 2y to get dy dx all the way by itself. And that reduces to just negative x over y. So this formula, this construction that tells us the relationship between changes in y and changes in x depends on both what the x coordinate and the y coordinate are. So for instance, as I said, this circle with radius 10, this point here, would be 0, 10. You can see that 0 for x and 10 for y makes this true. So at the point 0, 10, as expected, if you sub in 0 for x and 10 for y, I get negative 0 over 10, or 0. So thinking of another point, like, let's see, 3 for x and 1 for y. 3 squared plus 1 squared. Did I do that right? No. Let's see. What can I do with 8 and 6, I think is the point I need. Sorry, I was thinking of tens. So let's call this 6 for x, and no, that looks more like 8 for x and 6 for y. 64 plus 36, x squared plus y squared equals 100. So that would be a valid point on this curve. X is larger than y is, relatively speaking. That's why I swapped the variables at the last minute there. But if you see, so this formula at the point 0, 10, this has a value of 0. At the point 8, 6, you can see, oh, negative 8 over 6, otherwise known as negative 4/3. And that seems reasonable. Slope of a tangent line interpretation, or if I think about moving within this, a small circle around that point as x increases, which would happen to be going like, to the right, it would be going down for y. So that seems reasonable to have a negative slope there. And there's similar points in other quadrants, like let's see if I'm down here at negative 6, negative 8. I think that I should have a slightly negative slope there, not as negative as this, but there should be a negative slope there, or a negative rate of change as x increases, y decreases a little bit. And if I plug in these negative 6, negative 8, I'd get, again, 6 over negative 8, so negative 3/4. That fits with the idea of negative in terms of visual slope interpretation here. But in terms of overall, not bad. It should match up with our expectation there. Let's see if I can get this to go away. All right, so let's take a look at what would have happened if we'd done this a different way. So what if I solve this for y, just for comparison's sake? I'm gonna change colors here. So if I'd solved this for y first, which in this case isn't too hard, some of the equations, like the cubic example that we did on Tuesday, or last Thursday, would definitely be not pleasant. This one isn't too hard. Some equations you can't isolate precisely using regular algebraic means, weirdly enough. But in any case, this one, if I solve to get y by itself, I can see that I'd have y equals, it'd be plus or minus, to get both halves of the circle, the square root of 100 minus x squared, which, by the way, is not plus or minus 10 minus x. As you know, this would give us something curved. Plus or minus 10 minus x would be 2 straight lines, which is not what we want at all. So in any case, this is defined for x between positive 10 and negative 10, which, okay, that matches this. In this one, we didn't really have to worry about it, but if you tried to find domains, you'd find that x and y both vary between positive and negative 10. Same here. So if I wanted to find the derivative of this, though, dy dx, taking the derivative with respect to x on the left-hand side, on the right, well, I'm going to get this plus or minus. I'm just going to say that. That's like a negative, positive, or negative 1 coefficient multiplied onto the derivative of this. I'd get 1 over 2 times the square root of just our normal square root derivative, 100 minus x squared, and then times chain rule, derivative of what's underneath here, I'd get negative 2x. So simplifying this a little bit, the 2's drop out, and I'll have x over the square root of 100 minus x squared. And then I have a negative and a plus or minus, well, just plus or minus then. it's actually lots of times what you'll see done is like minus or plus, but regardless, you have this expression here, and you get two results then. For every x, you get two different results for what the steepness is, corresponding to, well, the top half and the bottom half. And in fact, it's in that reverse order. The negative corresponds to when you put in, yeah, it's still kind of a mess, like what corresponds to what, because you really do need to know, well, which XY point am I talking about? Because this gives me two coordinate points. So for any X value, I'm going to have the steepness at two coordinate points. So although you can find this expression, it's almost more confusing to use because it only allows you to plug in a single value of X, and not the whole XY point. So let's talk about then something else that we can do with these. So I said, let's prove some derivative rules that we learned earlier in the semester. So power rule says that if I have x to the n, let me just write it out here. Power rule. So if I have, I'll just use the simple notation instead of f of x. If y equals x to the n, then dy dx is just n times x to the n minus 1. And we worked that out in person with x squared and x cubed. And the book shows, like, if you have x to the fourth, fifth, sixth, any integer power, whole number power actually, that this works. We also showed that this works for n equals 1/2 power. But what we didn't show is that it works for negative powers. We didn't show that it works for fractional powers other than half. And well, that's kind of problematic. So let's see what we can do by rearranging this. Now, when we talked about this at first, we just had like a linear equation. I put everything on one side. I'm not going to rearrange this by putting everything on one side, but I am going to do an algebra step. The algebra step that I'm going to use is one that's going to be one that will allow me to rewrite the exponent in a different way using logarithms. So this is what's called logarithmic differentiation, using logarithms to help you rearrange an expression. And this isn't something that's going to be on your test, but I just want you to see, wait, I'm sticking extra letter. I just want you to see what some of the various uses of this are, because you will see this used all of a sudden in higher level math classes. Differentiation. Sorry. You'll see this used in higher level math classes. Just all of a sudden they take and use derivatives, or they use logarithms, and then have a completely new equation that they're working with. And that's a valid thing to do, because although y equals x to the n was maybe given, this is equivalent to taking logarithms of both sides. And I'm going to use natural log just because I like it, but it doesn't really matter. Natural log of y would equal the natural log of this side. And if you remember things about log properties, that would mean you can bring down the exponent, n times the natural log of x. So remember the rule of x here. N is supposed to be able to be any constant. It could be 0 also, in which case if it's 0, then this whole right side is 0, and that's fine because, well, we're anticipating zeros for derivatives anyway. But in any case, taking a look at this is equivalent to what's in the box up here. Those two mean the same thing. They express the same relationship in two different ways. So I should be able to find dy dx from this form, not using power rule, and figure out the relationship between changes in y and changes in x. So it uses logarithmic rule. If I take the derivative of natural log of not x with respect to x, it's going to involve chain rule. And I'm going to take the derivative of a constant times the natural log of x with respect to x. This right-hand side, that's a constant coefficient. And the derivative of natural log of x with respect to x is 1 over x. On the left-hand side, the derivative of natural log of y. Well, the derivative of natural log of something is just 1 over something. So I'm going to say 1 over y. But since this is a y and that's not a y, I need to use chain rule times the derivative of y with respect to x. So again, our final step is find dy dx, as in isolate dy dx. So multiply both sides by y. So if I multiply both sides by y, I have dy dx equals, well, I have n times 1 over x times y. So I'm going to write it like that for just a second. Now, this doesn't look like our standard result from power rule, but keep in mind what y was. Y is equivalent to x to the n. So if I replace that to have this written as a formula not in x and y, which isn't really needed because this is something that would be a function. Y is a function of x for any value of n. So if I rewrite this as n times 1 over x times x to the n, you can see that these two terms, 1 over x, otherwise known as x to the negative 1, and x to the n, this is reduces the power of x by 1. I can write this as x to the n minus 1 power. So I've got n times x to the n minus 1. And that is a result we were expecting. And this is permissible to take natural logs of these as long as I know what these x's and y's are. Now, there's just some other algebra difficulties. We'd really need to have absolute values on these, but that doesn't actually change the derivative rules. Natural logs of absolute values and natural logs of parentheses, x's and y's, are just the same. So it all works out okay. One other rule I want to show you, not related to using this logarithmic differentiation to rewrite, but just using rewriting an inverse function. We had all those inverse trig functions, and all of them can be done somewhat similarly to this, but they just have these ugly, weird expressions. This you will see again in Calculus 2, rewriting expressions relating trig functions and inverse trig functions to one another and to other relationships using triangles or circles, take your pick. But let me clear off this and we'll talk about the arc trig functions. So let's see, a new color. Let's say I have y equals arc sine of x. So arc sine of x is the same as inverse sine of x, meaning this, just another way to write this is x equals sine of y. If arc sine of x is y, then the sine of y is x. This is an inverse relationship that says these two things are true. Now, there's domain issues to keep in mind. The arc sine function, we only allow x to be between what, negative pi over 2 and positive pi over 2. It's first and fourth quadrant circle-wise. Just so that this does represent a function. So going back, this would have a restricted domain also. But regardless, if I think about from this format, find dy dx, well, I'm going to have x derivatives to take on both sides, which the left-hand side is going to be easy. And the derivative of sine of y with respect to x is going to involve chain rule. So 1 on the left-hand side, derivative of sine function is a cosine function of the same input, and then times dy dx. So finding dy dx would just be 1 over cosine of y. Now, that doesn't look particularly familiar, but this part, and this might actually be something you did in a pre-calculus course, it depends on your class, but in terms of rewriting, I had in the original, I had a sine of y, now I have a cosine of y, and I'd like to express either of those in terms of x. And here's the relationship between x and y. So you can do this in a circle or a triangle. I'm going to do this in a triangle here. So let's say that I have a right triangle. Now, when I'm thinking of trig functions and triangles, sine of something, the angle is what's in the parentheses. So this gets to be angle, that's a measurement of y. And the sine of angle y is supposed to be x. So thinking sine is opposite over hypotenuse, I'll do this the easy way, make the hypotenuse equal to 1. There, now I've got x over 1 is the sine of y, according to this. Now, like I said, you could do this in a circle also if you like the, want to think about something like this. And as long as I pick an angle that is in the first or fourth quadrant, it'll make sense relative to this expression we're going to get, or the expressions we should be working on. But same setup. The x, I just didn't want to draw it in the circle specifically because of the name of this and calling it x, and x would be this vertical side. But in any case, in this expression here, I have a way to write cosine of y in terms of x also. Cosine of y, so in this triangle here, sine of y is x over 1. Cosine of y, well, I have to work out the other side. Tangent of y, I could write any of those based on this circle, right? Well, all I'd need to write either cosine or tangent is the length of this other side. So a squared plus b squared equals c squared sort of relationship. Here's the hypotenuse. So this one squared minus that one squared is 1 minus x squared. Is this looking familiar? Cosine of y would be adjacent over hypotenuse, square root of 1 minus x squared. So our dy dx in terms of x is 1 over square root of 1 minus x squared, as expected for arcsine. You can do similar things with arc cosine, arc tangent, arc secant, and so forth. All of those can be proven using this method of write them as x equals the regular function in terms of y as the argument, and then use implicit differentiation. So that was some fun with implicit differentiation and how it works, both just a random equation, but also in help of actually proving things we just assumed to be true earlier on. Now, let's get back to some of the other types of applications. So I want to talk about related rates, which is something that you're going to see a question or two on your test. The test is next week, Thursday, and it is using the Respondus monitor. It's the browser and webcam. It uses less bandwidth than the Zoom feature did, so that's why we're switching to that. There are too many issues with people's tests freezing, webcams freezing, nothing working. So let me get us out of this. And I want to show you a keynote instead. Hold on. If it will let me. All right, let's see. Maybe. Too many things on top. All right, so let me just then recap the question we did at the end of class on Thursday. So we had the edges of a cube getting longer at a rate of 2 centimeters per second. And we want to know how fast the volume was changing at a specific point during that motion. So the idea is we start with an equation that relates the geometric quantities, in this case, edge lengths and volume. And then we take derivatives with respect to time, since we have these rates like speeds, derivatives with respect to time in order to relate how over time the two will change together. So if I look at this, I've got this rate of change, 2 centimeters per second. That's how fast the edge length is changing. So if I call the edge length, if I have a variable for this, this would be the derivative of the edge length with respect to time. What I want to know is how the volume changes with respect to time, maybe dv dt, when each edge is 50. And I'll figure out what to do with this later, but this is a measurement for the edge length. This is a rate for the edge length. And I want to find a rate for the volume. And all these rates are speeds, like rates with respect to time. So we have edge length, volume, and how fast either one of those is changing. But if I can relate edge length to volume, just the basic geometry, volume of edge length, and this, I used S when I was typing this up, volume of a cube which with edge length distance, S, is S cubed. Then if I take a derivative of both sides of this function with respect to not S, but with respect to time, I'll use T for that. As will your book, just kind of insert this T all of a sudden. Then, and you can write this as V of S or just plain V, either way. I think it's sometimes easier to leave out the function notation so that it doesn't look nearly as messy. But the derivative of V with respect to T and the derivative of S cubed with respect to T, neither of those are formulas that have T as their underlying variable. So in both cases, we're going to just use implicit differentiation. On this side, it's just literally the symbol dv dt instead of writing it this way. On this side, we get to use chain rule because it isn't just a linear variable, it's a cubed variable. So 3 times that side length squared, derivative of the cubed function, times the derivative of S with respect to T. So this relationship here relates how the volume changes, how fast, to how fast the edge length changes. And it involves knowing a third item as well in this case. It's not always the case that there's a third part to it, but this involves also knowing the side length. So you have to know 3 things. This relates 3 items. So in order to find one, you have to know the other 2. That's what this 50 is for. So if we substitute in, and we did this at the end of class on Thursday last week, we get 3 times 50 squared times 2. 2 is this 2 centimeters per second. That's the rate of change of the edge length, ds dt. So 15,000 cubic centimeters per second was the growth rate. It's positive, so growth rate of the volume as the edge length was growing at a rate of 2 centimeters per second. So let's take a look at something that's not a cube, but another geometric figure, a sphere. So pretending, we'll talk about a balloon that's spherical. Balloons aren't typically exactly spherical, but it'll be close. So let's say that after a spherical balloon is untied, it expels helium at a rate of 150 cubic inches per minute. We want to know how fast the radius is changing when the balloon has a volume of 500 cubic inches. So again, on this, I want to start by thinking about what's the underlying geometric relationship that we know, and then we'll take a derivative with respect to time so that we can relate the rates of change, speeds of something happening to one another. So like I was mentioning last class, I'm not going to anticipate that you or force you to remember every geometric formula you've ever used. For test purposes, for homework and quizzes, you have access to your notes and can look up whatever you want. But let's say that if this were a test, it would say, note, the volume of a sphere is given by 4/3 pi times the radius cubed. So this is the underlying quantities equation. It relates the radius of a sphere to the volume. So looking at what's given here, a spherical balloon is untied. It expels helium at 150 cubic inches per minute. This is a rate of change of, look at the units, cubic inches per minute. This is how the volume is changing, right? This is a volume per minute that it's getting expels, getting rid of. So the rate of change of the volume with respect to time is what this is. Now, I'm going to write down 150, but I'm missing something. So dv dt, this is the rate of change. Rates of change, remember, can be positive or negative. This is getting rid of helium. The volume is shrinking. by 150 cubic inches per minute. It's really easy to forget negative signs when you're dealing with decreasing quantities, because when we're thinking about increasing, we don't have to think about the positive, nor do you have to write it down. So just make sure you keep in mind if something's growing or increasing, you're talking about a positive rate of change. If something's shrinking or decreasing, that's a negative rate of change, and don't forget to use the negative sign. When you're writing out a sentence, you can use other words to indicate that. But for the purposes of doing our computations, we're going to need a negative in there. So this asks, how fast is the radius changing? How fast is the radius changing? That's asking us to, so if you maybe even just think of translating, it's asking us to find how the radius changes, how fast. So dr dt, I'm just using, again, the generic t for time, where in this case, our time would be measured in minutes, since that was the time unit that was used here. I mean, you could do unit conversions, but might as well not. So we're going to find dr dt, the rate of change of the radius, how fast the radius is changing. And notice, the balloon is untied. It's getting rid of its volume. So we'd expect this to be negative. So we're going to find the rate of change of the radius when the balloon has a volume of 500 cubic inches. So this is going to be like in the last question, that like when the side length is 50 or something. It's some extra piece of information. We'll likely need it, although sometimes there's extra unnecessary information given. But there is this is at a particular point in time during the process. I'm not going to use this information until the end, just like I'm not going to use this until the end. I want to start with a quantities equation, create a related rates equation, and then plug in numbers afterward. So this number is talking about a specific to this situation, not about volumes and radii in general. This is talking about a specific point in time during this situation, not about the relationship in general. So if I start from v equals 4/3 pi r cubed, and I want to know how the volume is changing over time and the radius changing over time are related to one another, I'm going to take derivatives with respect to t, time. So notice dv over dr, dv/dr is how the volume changes relative to the radius. dv over dt, which is how I'd write this left-hand side once done, is how the volume changes over time. The units give it away. It's cubic inches per minute. I've got to have, notice that the units in this match up with the fraction form here. Changes in volume, changes in time. Cubic inches, minutes. All right, so right-hand side, taking the derivative with respect to t of something that doesn't involve any t's. 4/3 and pi are constants. R is the thing that's a variable that changes over time. So taking this derivative on the right-hand side, I'm going to have 4/3 pi times 3, and I'll clean this up in a minute, but 4/3 pi, constant coefficient, times 3r squared, and then since it's a derivative with respect to t, not r, I need chain rule, times the derivative of r with respect to time. And what I mean by, I'm going to clean this up, this 3 and that 3, I can make this look a little bit less messy. It's not a big cleanup, but this gives us that dv dt, the rate of change of the volume, is 4 pi r squared times dr dt. So we started from, here's our quantities relationship. We took a derivative with respect to time, and a little cleanup gives us an equation that relates the rates of change, a related rates equation. So now we should be able to use this to help answer our question. After spherical balloon's untied, it expels helium at 150 cubic inches per minute. This is dv dt. This is a constant during this question. In the cube edge length problem, it's the edge lengths that were increasing at a constant rate, one rate throughout the problem. In this case, it's the volume that's decreasing at a constant rate throughout the problem. But using that then, I want to plug in dv dt is 150, negative. I want to find dr dt. This is our unknown. So I also have to plug in a value for r. It's going to be a little bit messy. So negative 150 equals 4 pi, because, well, we weren't given r, times dr dt. Now, dr dt is the thing I'm trying to solve for, so I expected to not have that. But I don't have the radius given. Luckily, we know the volume. And although it's not simple, I do have another relationship. If I know the volume, I know the radius. And if I know the radius, I know the volume. Those two are related directly. So although I have to use this equation to solve it, I already used it once just for something else. If the volume is 500 cubic inches, I certainly have a way to solve for the radius. It's just not a nice number. What, 500 times 3/4, so 1500 over 4, divided by pi, and take the cube root to get r, just fun with algebra. That would go in here. So to solve for dr dt, I'm going to have negative 150 over 4 pi times that lovely number, whatever it is, squared. And it will be negative. I don't know the value of it off the top of my head. If you want to pop this in a calculator and see a decimal value for this, you can. Sorry, I just didn't rewrite this whole expression in that spot. There's obviously other ways you could write this with exponents. I could say 1500 over 4 pi to the 2/3 power. That would maybe be a way to write it, or type it into something like iMathAS with slightly less difficulty, but realize that this denominator is going to be something positive due to that squared. And so the result for this is going to be something negative, as expected. So this one just inserted a little bit of extra trickery at the end, because instead of having the simpler, like, how fast is the radius changing when the radius is 36 inches, where you would just get to plug in a 36 here, it gave us the volume instead. But those two are related with general geometry, so we can solve this anyway. All right, let's take a look at another example. These are the steps we followed. We found the rates and the quantities, figured out how they're all related, just kind of interpreting or translating this paragraph. Write the equation for the quantities. Volume equals 4/3 pi r cubed. Take the derivative of that with respect to time to figure out how their rates of change over time per minute are related, and then plug in to solve. So here's a messier question. This one's going to involve a little bit of trig. I've got a motorboat leaving the shore going 28 kilometers per hour in a circular arc with a radius of 60 meters. I want to know how fast the boat's distance from shore is changing when the boat's traveled a distance of 150 meters around the circle. Sorry, I'm moving some of my toolbars out of the way so I can see this whole diagram. All right. So in this diagram, let's see. We've got some things we can label rather than redrawing it from scratch. Let's say that we've got this radius of 60 meters, just so we can figure out what on earth is being talked about here. So this circle has a radius of 60 meters. Motorboat leaves the shore going 28 kilometers per hour in a circular arc. So that's not the length of this, but that's a speed at which the boat's traveling along this arc here. So this is the speed at which the arc length is changing. Or the speed along the arc length, the distance that the boat is traveling. Now, one thing I want to mention about this, there's 150 meters, 60 meters. This one's in kilometers, which is a normal way to measure speed. But instead of saying 28 kilometers per hour, I'm going to change this to meters. 28 kilometers, 1,000 meters per hour. All right, so the speed that the arc length is increasing at, it is increasing, is 28,000 meters per hour. Now, luckily, it's not going to go on for very long. Notice also there's no times mentioned in any of these questions, like after 3 seconds, what's happening, or after 2 seconds, or after 3 hours. The time is just kind of used to measure the relative rates of change, but we don't need to know particular values of time. Excuse me. So, all right, so we've got this 28 kilometers per hour. That's the speed at which this line is increasing in length. The circular arc has a radius of 60 meters. How fast is the boat's distance from shore? So the boat's distance from shore, although the boat was traveling in an arc, the boat's distance from shore, we wouldn't measure on the path it's taking, its literal distance from shore, as in straight line distance. Let me just change colors here for a minute. Would be measured by this. This is its distance from shore. Let me call that y since it's a vertical line. But that way we have y is the boat's distance from shore, like straight line distance. And based on this picture, and if you do the computations, 150 meters, that's 2.5 radius lengths. So 2.5 radians is the measure of this angle here. I'm going to use theta for that angle just so I can refer to it as something. So y is the boat's distance from shore. That would be measured in meters, since everything else is. If I'm going to use theta in the 60 meters and 150 meters, let's see, the length of this around the arc. Let me use A for arc length. Let me write that in blue, if I can. So let's say that A is this arc length measured in meters. The speed of the arc length increasing, that would be dA dt, right? The rate at which the arc length changes over time. Again, just using a t to represent time that we're not really using, but our arc length is measured in meters. The boat's distance from shore can be measured in meters. A, here I'll label a diagram, is this blue curve. Y is that straight line distance to the shore. And I have this theta here that we didn't use over here, but in order to start this problem again, I'd need to relate the quantities. I want to know how fast is the boat's distance from shore changing. The distance from shore, let me change back to my appropriate color. dy dt is the rate at which the boat's approaching shore, or the rate of the distance from shore, the rate at which that's changing. And y at this point would be shrinking, right? So I'd expect this to be negative. Get rid of this little extra, there we go. So this dy dt, this is our goal, is to find this. We want to find dy dt. We know dA dt. I know what y and a are. Those are the things that are changing, but theta is also changing. And the reason is because I can't necessarily come up with right away an easy way to say how a and y are related. I have a rate of change for a, I want a rate of change for y. I know what a and y are, but either one of them I can relate to theta. So I'm going to use theta here to help write an equation that relates A and Y. So it's like we have a system of equations. A, the arc length, is just, well, it's the number of radius lengths along here. The radius is 60, and theta tells me the number of radians. So the arc length is 60 theta. So if I was one radius length along, it would be 60 meters. 120 meters for theta equals 2, 150 meters for theta equals 2.5. This is a particular value of A. I'm not going to use that till the end. This is a rate. I'm going to use that at the end. These are like things to substitute in later. But the 60 is fixed. It's not varying over time. This is just a construction. It's a measurement of the circle. Let's see. Oh, Y. That's the other part that we needed here. So Y is this vertical. So it's related to the sine of theta. But since this is in a circle that has a 60-meter radius, the Y value isn't just sine of theta, it's 60 sine of theta. It's scaled up. Cosine is the horizontal aspect, sine is the vertical aspect of any of these triangles you form, whether they're in first quadrant or otherwise. So it doesn't matter that theta isn't this angle. When we're talking about angles that are beyond 90 degrees, beyond pi over 2 radians, you might have talked in a pre-calc class about reference angles. We don't need to find what this reference angle is. This measurement here is the sine value of this angle, whether or not they're literally in a triangle together. Well, so I have to scale it up by a factor of 60 since this is a large circle, but in any case, Y is 60 sine of theta and A is 60 theta. So I should be able to write an equation that relates Y and A and doesn't have theta. Easiest way, instead of writing a theta here, I can write something about A, because this is a super simple equation to invert rather than inverting this one and having arc sines. I can say theta equals A over 60. So instead of writing Y equals 60 sine of theta, I can write Y equals 60 sine of A over 60. And here we have a relationship that relates Y and A. I know the speed at which A is changing. I want to know the speed at which Y is changing. So this is my quantities equation. Now I just need to differentiate this with respect to time, T, mystery letter, to be able to solve. So dy dt, taking the derivative of the left with respect to T. On the right, I've got this coefficient and I've got a sine function. Derivative of a sine function is a cosine function of the same thing. And then chain rule, times the derivative of this inside. Now, A over 60, remember, is the same as 1/60th A. So taking the derivative of this inside with respect to T, I get 1/60th times the derivative of A, which is dA dt. So just simplifying wise, I can 60 and 1 over 60, those are gone. So I can make this a little bit less messy to look at, but we have the relationship that we need, dy dt, the rate at which the boat's approaching the shore, could be calculated by finding cosine of the arc length over 60, and the arc length over 60 is 2.5, right? 150 divided by 60 at the point in time we're interested in, times dA dt. So this is where we'd substitute in the values that we know. This is our speed, 28,000, right? Yeah, dA dt is 28,000. A is this arc length, 150. So I'm doing cosine of 150 over 60, or cosine of 2.5. Multiply those together, and that's a pop it in a calculator sort of thing, or GC. But this should come out to be dy dt is approximately, and this cosine will have a negative value. Cosine of 2.5, if you can imagine, cosine of this angle, this is theta, cosine of theta is the x coordinate corresponds to going this far to the left. So it's going to be something negative. This does come out to be, let's see, I worked this out earlier someplace or another. I think it's like 22,000 something. Negative 22,432 approximately. That would be meters per hour. So otherwise known as approximately approaching the shore at 22.432 kilometers per hour. So this negative indicates the distance to the shore is decreasing. So I could say the boat's approaching the shore directly or is getting closer to the shore at a rate of 22.432 approximately kilometers per hour. So that's that messy problem. There are a lot of different things to think about in each of these. And so I want to present these all for a few different reasons. The first one, spheres versus cubes, slightly different math to deal with. But also there is that we had to solve for what's the radius that corresponds to the given volume. In this one, we had to relate this third variable, theta, this central angle of the circle, in order to relate the arc length and the sine value, 60 times the sine value, to one another. So let's see. Let's take a look at one more question for today. And this one's not going to be trig, but we're going to have some triangles. I'm going to clear off this. And we'll take a look at, let's see. This one. I apologize, this was copied from something and it's poor resolution. But so a street light's at the top of a 16-foot pole. I believe there's a question somewhat similar to this in your homework, but the solution method is different because it's different pieces of given information. But we've got a street light at the top of a 16-foot pole and a woman that's walking away from the pole with a speed of 4 feet per second. She's walking in a straight line. We want to know how fast the tip of her shadow is moving along the ground when she is 35 feet from the base of the pole. So no diagram given in this. It's not a simple geometric shape, but definitely drawing this and thinking about how shadows work, which may be hard, maybe easy, but let's say we've got, okay, street light. Street light, 16 feet tall. That's the tallest thing in the problem. There's a woman, I'm just gonna add details later. Woman that's 6 feet tall, less than half. That's a ways away. So this is not necessarily to scale, but at some point in time, she's 35 feet from the base of the pole, but she's walking away from it. Now, in terms of her shadow, how fast is the tip of her shadow moving along the ground? Well, so if the street light, shining light from up here, shines it in all directions, but the tip of her shadow, I can't really draw straight lines too well. The tip of her shadow is going to be that straight line that follows from the street light past her head down to the ground in a straight line. So the tip of her shadow, as she's moving along, as she's walking farther away, her shadow is moving also. But what I mean by that, her shadow is actually moving at a different speed than she is. So if you can imagine when this woman was close to the pole, her shadow would have been, really short. But somehow the tip of her shadow is now farther in front of her. And maybe you did this as a kid, but watch your shadow get really big really quickly as you walk away from a light source. So the shadow is really short and then shadow is taller, meaning her shadow as she's walking out this way her shadow length is growing faster than she's walking. So if she's 6 feet tall and this is 16 feet tall, we want to know how fast the shadow is moving along the ground if I know how fast she's moving along the ground. And they're both going the same direction. So maybe you can see this is kind of related to the same setup we've talked about a couple of times before with, oh, I've got similar triangles and I've got a couple of different lengths, which eventually I'll be able to talk about how they're related to one another. But let's say that I think about this big triangle with the streetlight and the tip of the shadow. And so thinking about that, I've got, well, this would be whatever length it is, it's varying. But if I call this distance that the tip of the shadow is from the light pole y, then I can talk about the rate at which the shadow is moving along the ground as the thing I want to find. Moving. So the rate at which the shadow is getting longer, because the tip of the shadow is at the end of this. So however fast y is growing, that'd be how fast the shadow is growing. Now, her motion is this part back here, but I can talk about all of this just kind of thinking about her distance from the pole is a part of this. Let's see, her distance from the pole, let me call that x. So back to this big diagram, if this is y and this is x, then this is y minus x. So x is her, like how fast she's moving away from the pole. It's not in a triangle, but that's okay. I can still use x and it'll show up elsewhere. So x would be her distance from pole, her distance from the pole. And dx dt is how fast she's walking away from the pole, which is 4 feet per second. So it happens to be a constant, but dx dt is a constant relating to her distance from the pole. dy dt is not a constant because it was, or at least it's bigger. It's bigger than 4. We'll figure out if it's a constant or not, if this shadow is increasing at a constant rate that just happens to be bigger than 4, or if it's increasing at increasing rates, or whatever's going on with this. But the shadow's distance from the pole, tip of the shadow's distance from the pole, is given by y, and that rate is dy dt. So the only tool we have to work with is similar triangles. And there's no triangle in this picture that has a side length of x, but that's okay because there's a side length that uses x. It doesn't have to be just plain x by itself. As long as it uses x, if I can relate x and y somehow in a relationship, I can take the derivative of that relationship and find these related rates of change. So thinking about the two triangles I do have, this just happens to be y minus x and 6. I can relate those two sides to one another in a proportion, whatever sort of proportion you want to set up. 16 is to y as 6 is to y minus x. I could do implicit differentiation from this form, but I'd rather not. I'm going to get it into at least a linear looking format. So cross multiply 16y minus 16x equals 6y. And we can do it from this form also, but this is such a simple equation. I just kind of want to solve this. 10y equals 16x, or y equals 1.6x. Like I said, this is such a, it's just a linear relationship between x and y, as it turns out. So guess what that means? The rate of change, if I take derivatives with respect to time, not really official notation writing this afterwards, but I take the derivative with respect to time and I get dy dt equals constant multiple times dx dt. So the rate at which the shadow is moving around the ground is 1.6 times the rate at which she's moving over the ground. So her shadow is moving at a constant rate when she's moving at a speed of 4 feet per second. So it's moving at a rate of 1.6 times 4. dy dt equals 1.6 times 4, which would be what, 6.4 feet per second. So she's walking away from the pole at a speed of 4 feet per second. The shadow tip is moving away from the pole at 6.4 feet per second. So it's moving faster than her, but at the same rate all the time, which is why it looks like it's getting farther and farther ahead of her. All right, so I'm going to stop at that for today because that was a lot of examples. But next time, what I want to do is have you, there's a poll. I put another poll in Canvas for like what examples you'd like to go through. The homework assignment, not the one that's due this Friday, which is just some basic implicit differentiation with XY functions, or well, XY relations, not functions. But homework number, I think it's 18, 19, whatever it is, there's 15 questions in it, and they're all related rates questions. So I want to go over several examples from that, just use some of the questions from your homework, and at least go through most of the way so you have an idea how to set up. So make sure you answer the poll, pick your favorite questions that you'd like to see done. So that means for Thursday, I want you to be thinking ahead. A, I hope you've already finished the homework that's due Friday. B, be looking ahead at what you think will be most challenging, or try the problems already that are due the following week, so that you can work on those and get some assistance at office hours and over the weekend. Because the following week, by the time Tuesdays come around, I hope that you've finished up that homework and you're already busy studying for your test. Next week, Thursday is your test, so like a week and a half from now. All right, that's it for today. I'm going to be here for office hours for a while if you want to stick around, but that is that. I'm going to clear off the screen, and if you have any questions before you go, feel free to ask. And I see some questions popping up. Let's see. Oh, one person asked, why didn't we use the 35? So it turns out, ooh, sorry about that. I was trying to slide this around. Turns out that the relationship in this one, dy dt and dx dt, was just given by dy dt equals 1.6 dx dt. It didn't involve needing to know a value of x, which is what this would be. So this was a value of x, and this was like y equals 1.6 x. By the time I take the derivative, there's no x's left since there's only a linear x. So we didn't have a spot to plug that in. It was a constant for all values of x. So no matter how far she was, this is one of those examples of extra information, no matter how far she was from the pole up to the point where it didn't reach her head anymore from interference of whatever, the shadow is always moving at that same rate relative to her.